CES has never been a place for scientific verification. It is a technology exhibition designed to showcase best-case scenarios, optimized for visual impact and investor excitement. Donut Labs' solid-state battery demo at CES 2026 fits perfectly into this mold. So why is a CES demo not a real battery product? On stage, everything looks flawless. The battery is cut in half but does not burn or explode. The LED remains lit. The numbers sound astonishing. A full charge in 5 minutes, an energy density of 400 watt-hours per kilogram, and a claimed lifespan of up to 100,000 cycles. In reality, battery demos at CES almost always rely on single cells or very small modules, handcrafted over long periods and tested under extremely gentle conditions. Charging rates are typically very low, commonly in the range of C20 to C50, to avoid triggering degradation mechanisms such as lithium plating, interfacial cracking, or dendrite formation. Thermal stress is almost non-existent. Mechanical vibration is absent. Manufacturing tolerances are irrelevant because the cells are not produced at scale. This environment has nothing in common with real-world electric vehicle batteries. Commercial batteries must endure repeated charging at C/1 to C/3 rates, wide temperature fluctuations, continuous vibration, and long-term mechanical stress. At the same time, they must be manufactured with production yields above 90 to 95% to be economically viable. A cell that performs well once on stage only proves that it survived the demonstration, not that it can survive reality. A CES demo demonstrates possibility. It does not prove manufacturability. So, how realistic are the battery performance numbers promised by Donut Lab? For these reasons, battery demonstrations at CES, including those from Donut Lab, should be understood for what they truly are: proofs of concept, not proofs of manufacturability.
Donut battery is designed differently. It's designed for 100,000 cycles. Now, that's not just better cycle life. That's an entirely different category.
Consider the 100,000 cycle claim. Lithium-ion batteries in smartphones and electric vehicles typically achieve only 800 to 2,000 cycles before significant degradation. Even the most durable LFP batteries reach roughly 5,000 to 10,000 cycles. A lifespan of 100,000 cycles is not a characteristic of electrochemical batteries. It is a characteristic of supercapacitors. Supercapacitors charge almost instantly and last extremely long because they store energy as static charge rather than chemical reactions. The trade-off is extremely low energy density, usually around 20 watt-hours per kilogram, far too low for long-range vehicles.
With Donut battery, we set a new baseline: 400 watt-hours per kilogram.
This is where the paradox emerges. Donut Lab claims an energy density of 400 watt-hours per kilogram, comparable to the best chemical batteries, while simultaneously claiming the cycle life of a supercapacitor. If true, this would imply the discovery of a material capable of undergoing high-energy chemical phase changes without structural degradation over decades. Put bluntly, if they had achieved this, they would not need CES. They should fly directly to Stockholm to receive the Nobel Prize in Chemistry. A far more plausible explanation is that theoretical values are being mixed with limited real-world operating conditions, or that Donut Lab is promoting a hybrid capacitor system incapable of delivering stable power under real driving conditions. In scientific analysis, the data that is omitted is often more important than the data that is shown. Donut Lab's presentation is filled with marketing language but remains silent on the fatal metrics that have destroyed countless battery startups. One major mystery is volumetric energy density, watt-hours per liter. Donut Lab repeatedly highlights gravimetric density, 400 watt-hours per kilogram, while barely mentioning volumetric density. This is a familiar sleight of hand. It is entirely possible to create a very light but extremely bulky battery, for example, using porous or hollow structures. Such a battery may achieve high watt-hours per kilogram, but if the pack is the size of a refrigerator, it is useless for electric vehicles. Avoiding discussion of volumetric density suggests that the solution may simply be too large to integrate into real vehicle architectures. Then there is the manufacturing yield nightmare. Donut Lab describes its electrolyte as clay-like. In a laboratory, scientists can manually shape each layer to near perfection. In a gigafactory, producing millions of cells per month, controlling thickness and uniformity of a clay-like material becomes a manufacturing nightmare. What remains of Donut Lab's battery once the stage lights are off? Battery history reveals a disturbing pattern. The most sensational promises on the CES stage often become the fastest disappearing ghosts in the real world. In 2018, Fisker shocked audiences by claiming solid-state battery patents capable of 1-minute charging and 800 kilometers range. The message was clear: lithium-ion was obsolete, and Fisker would leapfrog Tesla. After CES, there was no production line, no commercial cell, no long-term degradation data. Fisker eventually went bankrupt, and the solid-state technology never existed beyond presentation slides. Sakti 3 represents an even more severe case. The startup claimed solid-state batteries with double Tesla's energy density, enough to reshape the EV industry. Dyson acquired Sakti 3 for approximately $90 million, placing a major bet on the technology. Dyson was forced to cancel the entire battery program, admitting the technology could not be mass-produced with acceptable reliability. What worked in the lab collapsed inside the factory. Even QuantumScape, widely regarded as the most credible solid-state contender, has not escaped this pattern. Despite backing from Volkswagen and relatively transparent data, QuantumScape has repeatedly delayed commercialization. The reason is not that the battery does not work, but that the gap between laboratory success and large-scale manufacturing is far larger than originally anticipated. Yet history also suggests that failed timelines do not necessarily mean failed ideas. The realistic future of Donut Lab's battery, if it proves to be more than a staged demonstration, will not be in mass-market electric vehicles. Performance targets such as 400 watt-hours per kilogram, 5-minute charging, and 100,000 cycles cannot coexist within a single commercially viable EV battery system under known electrochemical constraints. This does not automatically invalidate the entire technology, but it sharply limits where it could realistically be applied. So if a battery technology can only prove itself on stage while refusing to disclose yield, failure rate, and degradation curves, should we call it an industrial breakthrough or just another carefully staged CES performance?